Okay, we were surveying the results of BCHM. The paper Existence of Minimal Models for Varieties of Log General Type. Okay, so we summarized the main theorems as follows, but again, these are just summaries of their actual theorems. So if f from x comma delta to b is a q factorial KLT pair, which is projective over b, and we suppose that delta is big, then any MMP with scaling terminates. So maybe to be more precise, these are kx plus delta MMP relative to b. Okay. So that's their main theorem, and the kind of amazing observation was that assuming that delta was big gives you a lot of tools to actually MMP with scaling terminates, when without this assumption we still have no idea. And then we sketched their argument for how theorem 1 implies this theorem 2, which is really the one that maybe most algebraic geometers at large will actually apply. So in the same setup, so x comma delta is projective over b, q factorial KLT pair. Suppose that either a delta is f big and kx plus delta is pseudo effective. Or b, that kx plus delta is f big. There should be an f here, so f pseudo effective. Then one, x comma delta has a log terminal model. Two, in the log general type case, then it also has a log canonical model. Which we showed earlier, if it exists, it's unique. Three, the log canonical ring is finitely generated. So here everything's relative to the base, so we have to take this relative sheaf of algebras. And four, any weak log canonical model is good. Meaning that abundance holds under these assumptions for these pairs. Okay, so we finished by sketching how theorem 1 implies this theorem too. Any questions about that part? Okay, and then there's a lot of corollaries of these theorems that I want to discuss. So corollary 1, we have finite generation in general. So let's say x comma delta is a projective KLT pair with no assumptions on delta being big or on kx plus delta being big, then the log canonical ring is finitely generated. In particular, this is true for the canonical ring of a smooth projective variety. So the remarks here are that there are no assumptions on delta or kx plus delta being big. So what this means is that in general, we can always, for a KLT pair, we always have a proj of its canonical ring. The thing we don't know in general is that we obtain the proj of its canonical ring by first applying a sequence of minimal model program, by first applying a sequence of extremal contractions and flips, and then taking a base point free linear series from the log canonical. So basically, once you have finite generation, you know you have something that you might call the log canonical model, though it's not a birational model in general. It'll be lower dimensional, but you know you have something that's proj of the log canonical ring. But the point is that we can't understand it via the minimal model program without proving the conjectures in the general case. Okay, but the proof of this, essentially this is a theorem of Fujino and Mori that the log general type case implies this case. So the proof is basically that so theorem 2 above implies this in the case that kx plus delta is big. And now we want to reduce the general case to the case where kx plus delta is big. And so the idea is to look at, so again, this is an idea of Fujino and Mori. So we look at the base point, the linear series induced by some large multiple of the log canonical. So basically take the Itaka vibration. Take the limit as d goes to infinity and Stein factorize until it stabilizes. And so we get this rational map to z. So it has base points, just some rational map. But then we can resolve this rational map by some y. And now we can add divisors to the strict transform of delta. So that we have a pair y comma delta y, such that this map f, let's call that map f, the other map phi, so that the map f is crepant. So our usual assumptions, so 1, the pair is KLT, 2, the pullback kx plus ky, pullback kx plus delta is ky plus delta y. And 3, push forward of delta y is delta. And then maybe a few more assumptions as you wish. You can assume that it's actually a log resolution. instead of just a resolution of the rational map, and some assumptions about how these divisors meet each other. But the point is we can log resolve and pick the right divisor so that the log canonical ring of kx plus delta is equal to that of ky plus delta y. Noting that when we add exceptionals of f, so f is some birational map, so when we add these exceptional divisors, if we're only adding effective exceptionals to produce delta y, which is guaranteed by these conditions, then it's not changing the log canonical ring. So now we've reduced to, now we want to show that the log canonical ring of y is finally generated. And now we have a morphism down to the z. So what are the properties of this morphism? Well, the first observation is that the dimension of z is the Kodaira dimension of, or the Ataka dimension of kx plus delta, just by construction, because z is the image of the Ataka vibration for kx plus delta. And now the second observation is that phi is a k plus delta trivial vibration. Because if we look at the Ataka vibration on x, well, it's induced by kx plus delta. So on the generic fiber, since kx plus delta on the generic fiber is pulled back from z, then you can imagine on the generic fiber, kx plus delta is trivial, and so then we resolve and add the right divisors, and we get that on the generic fiber of y, kx plus delta is trivial up to whatever we had to blow up to resolve. So maybe there's some kind of horizontal blow ups we have to make. So I'll put quotes around here because there's a slight correction term to that. And that comes up in the Fujino Mori paper. But if you remember in the case of surfaces, when we had these k-trivial fibrations, these are the elliptic surfaces. And one of the things that we sketched for elliptic surfaces is that they have a canonical bundle formula. That if you have an elliptic vibration, then you can compute the canonical bundle as a pullback from a specific log canonical divisor on the base curve. And that's what Fujino and Mori prove in general. They prove a canonical bundle formula in higher dimensions for these kind of log analogs of k-trivial vibrations that essentially says that for this map phi from y to z, we have that ky, I don't know why that keeps coming up. We have that ky plus delta y is q equivalent over f to the pullback. I guess I don't need to put over f because I'm already adding a pullback. So it's q equivalent to the pullback of kz plus l plus b prime. Basically where this L and B are some specific divisors, and they tell you what L and B are, but we're not going to go into that in this class. But L, if you remember from the elliptic surface case, L was roughly measuring the way the fibers of F vary in moduli. And B was measuring the singularities of the fibers. So in the case of elliptic surfaces, L was related to this Hodge bundle that we got from pushing forward the relative canonical of our elliptic curves, and B was related to the multiple fibers, the non-reduced fibers that were a non-reduced multiple of a reduced fiber. And then in their formula, there's this extra B prime, and that has to do with what I put in quotes here, that it's not that you want it to be a k plus delta trivial vibration, but it's not quite, because maybe there are some blowups in F where you have to blow up some kind of horizontal stuff, maybe. Vertical stuff. But there's some extra correction term, B prime. But the point is that the existence of such a formula lets them conclude that the log canonical ring of ky plus delta y is equal to the log canonical ring of kz plus l plus b. And of course, here you have to check that you can pick this L and B so that the pair Z comma L plus B is a KLT pair. But that's part of their work. And so now this is the log canonical ring of a variety of log general type, because now Kodaira dimension of kx plus delta is equal to the Kodaira dimension of ky plus delta y is equal to the dimension of kz plus l plus b, which is dimension of z. Well, on the other side is dimension of z. So now we're in the log general type case when we go down to z, and so this is finally generated by BCHM. Or by their main result. And so then we have finite generation for log canonical rings in general. Didn't need to do that. Okay. Any questions? Okay, so that's the first important corollary for birational geometry. So this is a big conjecture for a long time. The next one is what happens when kx plus delta is not pseudo-effective. So in this theorem, we're either assuming kx plus delta is pseudo-effective, or it's big, in which case it's pseudo-effective because in fact it has lots of sections. In fact, it's effective. So you can ask what happens in the non-pseudo-effective case. So our minimal model conjectures tell us that in the non-pseudo-effective case, we should get a Mori fiber space. And they prove that this is in fact the case. So again, f from x comma delta to b as above. Suppose that kx plus delta is not pseudo-effective. Then there is a minimal model program over B such that you end up with a Mori fiber space. And here again, we don't know that every MMP that you can run on x comma delta terminates in a Mori fiber space. That's still a conjecture, but they tell us that there exists some MMP that terminates. Specifically, you can pick an appropriate MMP with scaling that terminates in a Mori fiber space. And this is interesting because you might think that if their main theorem is about the case where you have some bigness lying around, then this case where kx plus delta is not even pseudo-effective might be difficult, but somehow it's easier than the intermediate case where kx plus delta is pseudo-effective, but nothing is big. And we'll see why in the sketch. So pick some ample relative to B, so pick an F ample, such that kx plus delta plus A is F ample. So make A very large so that when we add kx plus delta, it's still positive. And such that the pair x delta plus A is KLT. And now we're going to consider the log canonical divisor kx plus delta plus epsilon A. For epsilon small but still bigger than 0, then this divisor is not pseudo-effective. And that's because kx plus delta itself is not pseudo-effective. So if we perturb it by a very small ample, then we're not going to add enough sections, or we're not going to add any sections to make it pseudo-effective. We have to add a large multiple of an ample to make it have sections. So we're just going to pick a small epsilon, but still not 0, so that it's not pseudo-effective still. And now we're going to run an MMP with scaling for kx plus delta plus epsilon a, but with scaling by a itself. Because if we note here, delta prime, if we just define delta prime to be delta plus epsilon e, epsilon a, now this is a big divisor. Because we have an ample plus effective. So this is a big divisor. So now we're in the setting where MMP with scaling terminates. And so now we'll run a kx plus delta prime MMP with scaling, where we're scaling by a. And so now this terminates by the main theorem. I guess what I labeled theorem 1. But because kx plus delta prime is not pseudo-effective, it has to terminate in a Mori fiber space. But now the point is that this kx plus delta prime MMP was actually also a kx plus delta MMP. And the reason for this is that we know that a is ample. So when we add this epsilon a to our boundary divisor, when we look at kx plus delta plus epsilon a, if we have any curves that are negative for kx plus delta plus epsilon a, well, the a part is strictly positive. And so kx plus delta is still negative on those curves. So any kx plus delta plus epsilon a negative curves are also kx plus delta negative curves. And so the kx plus delta prime MMP is also a kx plus delta MMP. And so we've produced a kx plus delta MMP, which terminates in a Mori fiber space. Okay, and I should remark here then that, so what's the case that's still open? It's when kx plus delta is pseudo-effective, but neither delta nor kx plus delta are big. And by open, I mean that's the case where we don't know that there exists MMPs that terminate. Of course, even in these other cases, we don't know that every MMP terminates. That's also open, but in this case, we don't know in general that that there exists an MMP that terminates. And you might ask, kind of what's wrong with this proof in this case? Like, why can't we still just take kx plus delta that's pseudo-effective, but where neither delta nor kx plus delta are big, and perturb it by an ample and try to run the same exact argument? The issue is that if kx plus delta is pseudo-effective, then when we perturb by an ample, we actually are changing the situation a lot. For example, if kx plus delta is trivial, and we add epsilon times an ample, suddenly kx plus delta is ample. So we've gone from the Kodaira dimension 0 case to the Kodaira dimension to the general type case as soon as we make any perturbation. Here we use the fact that kx in this corollary, we use the fact that kx plus delta is not pseudo-effective to say that when we perturb it by an ample, we're still in the same case. And so this type of proof, at least as is, can't work in this pseudo-effective but no bigness case, because now we're completely changing the Kodaira dimension when we do this perturbation. Okay, so one more important corollary to birational geometry. let's say we have a KLT pair x comma delta, and f from x to z is a kx plus delta flipping contraction. Then the flip exists. Okay, and proof. We know that the existence of a flip is equal to finite generation of the log canonical ring, or equivalently is equal to the existence of log canonical models. So or another way of saying it is the flip is like the question is, does the log canonical model of x comma delta over z exist? So we just need to show that the situation of a flipping contraction falls in the case of existence of log canonical models that BCHM proved, and that's not so bad. So by assumption, minus kx plus delta is f ample. That's what it means to be a flipping contraction. And so we can pick some divisor in this linear series, maybe some large enough multiple. So pick some effective divisor d that's equivalent to kx plus delta. And now we'll consider the pair delta prime is delta plus epsilon d. So now x comma delta prime is KLT for small enough epsilon. And delta prime is big because it's ample plus effective. So it's f big. And then finally, and here I should say it's f ample, so this is f equivalent. And then finally, kx plus delta prime is numerically equivalent to 1 minus epsilon times kx plus delta. And so the log canonical model for kx plus delta prime is the same as the log canonical model of kx plus delta. And so and this latter exists by the main theorem. Okay. So we have flips in general. So I want to say a few words about the induction that they have to do to actually prove this theorem, because so we briefly mentioned it a few times that the kind of the techniques that we have are that you take some divisor with coefficient 1 and you use a junction to restrict everything to that divisor, and then you hope that your MMP on the ambient variety has something to do with MMP on your divisor, and then try to use induction to say that you know everything about MMP on your divisor to say something about the MMP on your ambient variety. That's one of our methods. And the other method was to use MMP with scaling, which we said that termination of MMP with scaling is equivalent to finiteness of models. And so the way they actually carry out this strategy is by a very delicate induction, where they have to kind of separate each of these types of statements about existence of models and various about existence and finiteness of models and existence of special flips and termination of MMP in lower dimensions, and they have to kind of weave together this this delicate and beautiful induction to build up the whole theorem. So I wanted to kind of summarize the actual results that they prove, that they prove by induction on dimension, that then combine to give you these main theorems. So the first one is existence of PL flips, which we already spoke about last class. So I'll label them in the same way that they label them in the paper. So what they call theorem A is existence of PL flips. Theorem B is what they call special finiteness of models. Okay, so what's roughly the setup here? So if we have, well, everywhere we'll have the same general assumptions that f from x comma delta to b is a KLT pair projective over b. And now here, basically, they say, suppose that your divisor is of the form s plus delta prime, where s is some integral of a divisor. So this is the thing that we want to use for our induction. And suppose we're running through, suppose now we let delta vary. Actually, let me write this a little differently. Let's write it as s plus a plus delta prime. So where s is some integral divisor and a is some fixed ample. So we're in the case where delta is big. So we know we can write it as ample plus effective. Let's look at the divisors of the form some fixed ample plus some fixed s and then plus delta prime. And let's let delta prime vary. So basically they say that as delta prime varies over all divisors such that, well, it has to be effective and such that x comma delta delta of this form s plus a plus delta prime is still satisfies these assumptions that it's KLT and projective over b. Then there are finitely many birational models of x such that any log terminal model of x comma delta over b as delta is varying. So again, we're studying all the models in this polytope of all possible deltas to satisfy this condition, so that any one of these log terminal models is, and I'm just summarizing here. The result is much more precise, but is isomorphic to one of our finitely many. In a neighborhood of S. Okay, and so basically this says kind of, if you're running an MMP with scaling that's only changing things in a neighborhood of S, then you only have finitely many models. And this is usually in this field special finiteness, special termination, PL flips, or you can think of as special flips. These are ones that are kind of set up where you have an integral divisor S that you're going to induct it on, and like all the action is happening around S. So that's usually what special means in the MMP. So B was special finiteness, and then C, where did I write it down? C is existence of log terminal models under all these assumptions. Under these bigness assumptions. D is a non-vanishing theorem, just like similar to the non-vanishing theorem that we proved in class, but much more general. So they show that if kx plus delta is pseudo-effective, again under these assumptions. So if delta is big and kx plus delta is pseudo-effective, Well, non-vanishing is supposed to tell us that there are sections, and so basically that kx plus delta is actually effective. So it's equivalent to some effective divisor D, with the one caveat that here you have to work with R divisors instead of Q divisors necessarily, but that's some technical point. Okay, so D was this non-vanishing, and then E is general finiteness of models. So again, same idea. If you let delta equal a fixed ample plus delta prime, then as delta prime varies over all possible divisors, such that x comma delta is KLT, there are only finally many models. And then finally, the last part is the actual finite generation of the canonical ring result, plus a certain what they call Zariski decomposition, which is a decomposition of the log canonical divisor in a special form that lets you understand the base locus essentially of the sections. But I won't write down the details of the Zariski decomposition result. Okay, so to recap, the main results that are woven within each other to actually do this induction are existence of PL flips, so we need that to begin running the minimal model program. Special finiteness, finiteness of models if you only care about what's happening in a neighborhood of some divisor S. Existence of log terminal models. This non-vanishing, that if kx plus delta is pseudo-effective, then it's actually effective, at least under the big assumptions. Finiteness of models in general, and then finite generation. And then the induction proceeds as follows. So they show, well, this is actually from a previous work that we discussed the other class, that basically MMP in dimension n-1 plus just MMP in dimension n-1 implies PL flips in dimension n. So this we briefly discussed the other day. And then they prove that special finiteness in dimension n. So this subscript just means that we assume the theorem holds when x has dimension whatever the subscript is. So special finiteness in dimension n plus PL flips in dimension n-1 implies the existence of log terminal models in dimension n. I'm pretty sure I flipped around these indices. This should be special finiteness in dimension n, because x is dimension n. Now I'm actually confused. Did I flip this around? I think these should both be n. Okay, I think these should both be n, but I will check after class. And then finiteness of models in dimension n-1 implies special finiteness. In dimension n. So I should say, okay, so a few words, I guess. So this This first one we talked about the other day. Well, this one we want to be able to run a minimal model program with scaling and see that it terminates. And so we need PL flips because maybe we can hope that you can pick a minimal model program, so you only have to do PL flips. So you need at least existence of PL flips to continue your minimal model program. And then we showed that, or we observed that MMP with scaling terminates if and only if you have finiteness of models. So if you can rig your particular MMP with scaling so that you only need special finiteness for that particular MMP to terminate, then you get existence of log terminal models. So that's roughly the idea there. Here, we use a junction. So you say, well, I want special finiteness. So I want to know that there are finitely many models in a neighborhood of S. But these any model, like if I take any model on X, then if I look at a neighborhood of S and then I restrict to S, I get a model on S. And so you want to say that because there are finitely many models for S, then there's only finitely many special models for X, roughly. So that's using a junction. And then the next piece of the induction is non-vanishing in dimension n-1 plus special finiteness in dimension n plus the existence of log terminal models. They show implies non-vanishing in dimension n. And again here, how do you prove a non-vanishing theorem by induction? Well, you want to just say that I use Kalamata-Vivek vanishing to be able to lift my section. So I take my log canonical, I restrict it to one of these divisors S, then I get the log canonical for S with the different. Then I assume that there I have non-vanishing, so I have a section. And then I just want to say, well, then I have a vanishing theorem that tells me that I can lift that section up, and so I have a section upstairs. And the point is that this is not actually true. You might have to do some birational modifications to get into the situation where you can actually apply this lifting argument, and that's where you need this special finiteness and log terminal models in dimension n to make appropriate birational modifications and track what's happening so that you can actually apply this lifting argument. And then log terminal models in dimension n plus non-vanishing in dimension n. They show implies finiteness of models in dimension n. This one I don't really have a good way to give the idea for, but that's what they prove. And then finally, everything altogether implies finite generation plus Zariski decompositions. And so now we're back kind of at the beginning, but now we know finite generation dimension n, and so now by induction, we can get it for all dimensions. Okay, so that's all we'll say about BCHM. For the last 25 minutes, I want to move on to talking about non-normal varieties. So far in the class, we've always worked with normal and irreducible varieties. So now I want to say a few words about how you start applying the techniques of the minimal model program to non-normal varieties, and namely which non-normal varieties should you even be looking at if you care about birational geometry. So first, kind of why should you look at non-normal varieties? You can always normalize if you care about things that are happening at generic points. There's two reasons, and they're quite related. So reason one, if you want to apply these type of inductive arguments where we have this divisor S with coefficient 1, and we use induction and adjunction to actually prove something about our ambient variety, if we want to apply this to the log canonical case, where basically all the results of the minimal model program are still completely open, but are conjectured to be true, then you need to work with non-normal varieties. So it's also in some sense true that you do need to do that in the KLT or DLT case, but in the DLT case, each component of S is at least normal. So maybe S isn't normal, but it's only because it's a union of some normal things. But in the strictly law canonical case, each of the components themselves can have self-intersection and can have worse singularities and don't have to be normal. So if you want to use this induction, you have to understand something about law canonical rings and law canonical models of non-normal varieties, or at least what's the appropriate way to go from the non-normal S inside of X to its normalization. How do you translate between the two? And then the second reason, which is actually quite related and which we'll talk about on Wednesday, is to construct proper moduli spaces of varieties. So basically, we'll spend the final class talking about this application 2. Today, we'll set up by saying exactly which type of non-normal varieties we should be looking at. But really, these reasons 1 and 2 go hand in hand, because we'll see that the idea behind coming up with the right definition for moduli of higher dimensional varieties comes from this one, comes from looking at if you have a law canonical model and you have a divisor S, what kind of singularities does S have? Okay. So with this motivation out of the way, we need to set up some divisor theory on non-normal varieties. So we can still define Weil divisors as formal linear combinations of codimension 1 points on your variety, but we need one extra condition to have any hope of having a good divisor theory. We need to look at divisors D. So we consider D such that the generic points of D, or let's assume it's a prime divisor, so D is irreducible, so such that the generic point of D lies in the smooth locus of X. So in particular, we should assume X is reduced. So even in the non-normal case, we'll always assume that X is reduced, but not necessarily irreducible. But okay, if it's reduced, it has some open subset where it's smooth. And now we're going to consider prime divisors whose generic point is in the smooth subset. And the reason is that we want to be able to measure order vanishing along prime divisors. And the way we do that is by looking at the local ring O of generic point on X. And so the condition that X is smooth along the generic point of D exactly tells us that this local ring is a DVR, and so we can talk about order vanishing along our divisor. If we don't have that, then we basically can't do anything. So now we can talk about Weil divisors as formal linear combinations of such prime divisors, and we can talk about linear equivalence in the same way as in the normal case, as long as we stick to considering only these types of divisors. But then we also need to consider we need to have a good notion of Weil divisorial sheaves associated to these divisors. And if you remember from the normal case, the main thing we had about these sheaves is that their sections were determined by what happened away from codimension 2. And this is important because this is how we define the canonical bundle. Without this condition, it doesn't necessarily make sense to even talk about the canonical bundle. But with this condition, we said that on a normal variety, you take the canonical bundle on the locus where it makes sense, and then you push it forward. And because sections are determined away from codimension 2, this push forward is some sheaf that's uniquely determined and gives you a canonical Weil divisor. Now, on normal varieties, this isn't always the case, and so we need to impose a condition. So we need to assume that X is S2. So this is one of Serre's conditions. So normal varieties are automatically S2. And in general, Sn is the condition that at any point the depth of the local ring Ox comma X is greater than or equal to the minimum of n and the dimension. So if you're familiar with things like depth and things like Cohen-Macaulay, then this is saying that kind of Cohen-Macaulay means the depth is equal to the dimension for all points. And here it's saying that you have this kind of locus where it's Cohen-Macaulay, and then in higher codimension, you're bounding the depth. It can't get too small. But for us, what's important about S2 and an essentially equivalent characterization of S2 is that if you have a function defined away from codimension 2, then it uniquely extends. If you have a variety that's not S2, this no longer holds. If you want to think about an example of a variety that's not S2, consider two planes in A4 meeting at the origin. So maybe the vanishing of the X and the Y coordinates and the vanishing of the Z and the W coordinates. This union is not S2 because I can have a function that's defined away from the point of intersection where it has one value on one of the planes, a different value on the other plane. And so it doesn't extend, even though it's defined away from codimension 2. So this is exactly the type of thing where we want to throw out so that we can talk about Weil divisorial sheaves by defining their sections on some big, large, nice open locus. Okay, so we need S2. We need to talk about divisors whose generic point is in the smooth locus. And then we need to talk about the canonical sheaf. And so we already said our strategy for the canonical sheaf, just like in the normal case, is to take the canonical sheaf on some open set where it's clear what it is, and then push it forward and use the S2 condition to say that its extension is some unique, nice divisorial sheaf. So to do that, at the very least, we need to assume that we have a large open set where the canonical sheaf makes sense. And so we need the condition, what's usually called G1, which is Gorenstein in codimension 1, which means that there exists an open set U in X such that the complement has codimension 2, or at least 2, and 2 such that U is Gorenstein, so it has a canonical line bundle. Okay, and again, this was something that is always true for normal varieties, and this was what we did to define the canonical on a normal variety. We said take the smooth locus, it has a canonical, push it forward. And so now, so the upshot is if X is reduced G1 and S2, we can define omega X to be the push forward of this inclusion from such an open set of omega U, which is some S2 sheaf, and this sheaf has to be of the form sheaf of sections of some canonical divisor, where Kx is a divisor satisfying the properties above that each of its components has generic point in the smooth locus. Okay, so at the very least, if we're considering non-normal varieties, they need to be reduced G1 and S2. Now in this case, yeah, let me say a few words about what happens when we take the normalization, because that's a natural thing we can do. So let's assume now from now on that X is reduced G1 and S2, and let's take the normalization of X. Now we can ask what happens to the canonical divisor when we pull back to the normalization. And so this is described by the conductor, or in general, the conductor basically tells you how you go from the normalization to X itself. So the conductor is an ideal defined as follows. We have an exact sequence 0 to OX to the push forward of the normalization to something. Let's just call it F. What's F? Well, F is some sheaf supported on the non-normal locus of X. And the conductor is the ideal, which is defined as the annihilator of F in OX. So it's an ideal in OX, but in fact, it's also an ideal in OXN. So of course, it's contained in OXN just by this exact sequence, because OX is a subalgebra of OXN. But the upshot is that the conductor is actually an ideal of both rings. And you can think of it as, if you work locally, you can think of it as the functions on. Sorry, here I should write xn. So it's the functions on xn. One second, wait. Do I want to write xn? No, I want to write ox. Sorry. Yeah. It's the functions on ox, so that when you multiply them by a function on oxn, because of course, so oxn is a module over ox. So when it's the functions in ox, and when you multiply them, so when you multiply a function on oxn by these, you always get back to ox. Maybe that's the best way to write it. That's its description locally. Okay, and then so you can check that it's an ideal of both OX and OXN, and this ideal cuts out a divisor, which is the vanishing of the conductor, or in general, it cuts out some subscheme. D, which is the vanishing of the conductor on XN. And now the upshot is that the pullback under these assumptions, under this G2 and S1 assumption, or sorry, G1 and S2 assumptions on everything, then the pullback of the canonical on X is equal to the canonical on XN plus the conductor. So this is some. I think this, at least on the large open set, this follows by growth-unique duality. So on the large open set where everything's a line bundle. And then because that open set is complement codimension 2, then this equality on this Gorenstein locus extends to an equality on everything. And here maybe you have to be a little careful, because under these assumptions, it's possible, at least a priori, it's possible that D might have some components that are non-divisorial. So when I write this this expression, I mean take the divisor part of D, throw out any codimension 2 parts. I don't remember off the top of my head if S2 is good enough to ensure that D only has divisor parts. I'm not 100% sure about that. So for now, assume that we've thrown out any piece of the vanishing that's not a divisor. So this formula makes sense. Okay, so that's how we compare the canonical divisor downstairs and upstairs. We have to compute this conductor. But now we're not quite done. We're not just going to stick to reduced G1 S2 varieties, because if we go back to our motivation really comes from the properties that this non-normal components with coefficient 1 in our boundary for a log canonical pair satisfy. So actually these S are a little nicer, and this comes from computing the surface case. So here's an example, or maybe a lemma. So if X is a surface, D is a reduced divisor such that X comma D is log canonical, then D has at worst nodal singularities. So basically any divisor with coefficient 1 on a log canonical surface is at worst a nodal curve. And so this tells us that actually, instead of looking at all G1 S2 varieties, we can actually look at the smaller class of varieties that are nodal in codimension 1. Because, so I'll leave this as an exercise. But now if we look at the general case, if we have an X comma D where the dimension of X is greater than or equal to 2 with D reduced, and X comma D log canonical, then we can localize the codimension 2 points of X, reduce to the surface case, and so we see that at every codimension 2 point of X, D is at worst nodal, but codimension 2 points of X are codimension 1 points of D, and so we get that D is nodal in codimension 1. And so now we've pinpointed the class of singularities we want to look at. We want to look at an X. Okay, so then from the point of view of MMP, the natural non-normal class of varieties to look at are X such that 1, X is nodal in codimension 1. So, well, maybe 0 it's reduced. First, it definitely has to be reduced. Nodal in codimension 1. And if you remember, nodal curves are automatically Gorenstein because they're, for example, planar curves. So they have so by junction, they have a canonical line bundle. And so if you're nodal in codimension 1, then in codimension 1, you look like a nodal curve cross something smooth. And so you're also Gorenstein in codimension 1. So that automatically takes care of that. But these are some much smaller class than the general Gorenstein in codimension 1. Okay, so we want to reduce variety, nodal in codimension 1, and we need it to be S2. And this is a starting point. This is the analog of normal varieties in the non-normal case from the point of view of MMP. Now, finally, we have the setting where we can talk about the canonical divisor, we can talk about V divisors, we can talk about orders of vanishing, so we can hope to talk about discrepancies. The last thing is that we need whatever our choice of log canonical divisor is, we need it to be Q Cartier. And so now we can give our definition. A pair X comma delta is semi-log canonical if I skipped ahead too much. We need to check one more thing. Sorry about that. So I have 4 minutes. Okay, great. So let's say that we're in this case where we're nodal in codimension 1. Let's study what the conductor looks like in this case. So we saw that the conductor measures how the canonical changes when we pull back the normalization. So let's compute it in this nodal case. So the computation of the conductor is local. So if you want, you can compute it by studying the case of kxy mod xy. And its normalization, well, its normalization is just two smooth branches. So this is that's the normalization on coordinate rings. Or geometrically, this is like you take a node and now you pull them apart, so you have two smooth branches. So now you can compute either algebraically what happens here, or you can think about the global case of a single node inside of say a nodal cubic. I think that case is easier for me to think about because the conductor is something local around the singular or around the non-normal locus, but if we compute it in this example, then we'll see what the conductor is, and that'll tell us. I mean, it'll be supported in over the nodes, and that'll tell us what it is. So if you compute it in this example, let's call this C. Its normalization is P1. Then the pullback of the canonical of C, well, it's the canonical of P1 plus some correction term. And what's that correction term? Well, we already saw it in an example for a junction. It's the sum of the 2 points that are glued together to give you the node. And the thing to note is that they're reduced points. They come with multiplicity 1. And they're exactly the points you glue together to produce your non-normal singularity. And so in this case, we call, so in the nodal case, and thus in the nodal and codimension 1 case, because everything's determined by the codimension 1 behavior, we call the vanishing of the conductor the double locus, because it's the locus on the normalization where the normalization map is 2 to 1. And that's all we like. Generically, it's 2 to 1 on the singular locus because we're assuming nodal and codimension 1. And the upshot is that this computation tells us that this double locus is a reduced divisor on the normalization. And so if we want to understand, so if we have some pair x comma delta, and we want to understand kx plus delta, this corresponds to kx plus the double locus plus the strict transform of delta on the normalization. And because the double locus comes with the reduced scheme structure, they're reduced divisors, then we don't have to worry. This is still a boundary in our sense because we're adding these divisors with coefficient 1 on xn, and that's still a boundary. The issue is like if you had worse non-normal singularities like cusps or something, then this vanishing of the conductor would be some non-reduced divisor. And then when you pull it back, you wouldn't get some boundary pair upstairs. But because we're assuming nodal in codimension 1, we actually always have a boundary pair upstairs. And so now finally we can give our definition. X comma delta is semi-log canonical if 1, x is nodal in codimension 1 and S2. 2, kx plus delta is Q Cartier. So we need Q Cartierness talk about pullbacks, to intersect with curves. Everything we're doing needs Q-CARTA, just like in the normal case. And 3, the pullback to the normalization. If we write the pullback to the normalization as kxn plus delta n plus the double locus, then we have to assume that xn delta n plus the double locus is log canonical. And now to study semi-log canonical pairs, we can, like the basic strategy is take the normalization, add the double locus. By assumption, upstairs things are log canonical. Try to apply a minimal model program upstairs, and then try to undo the normalization. Try to glue back down to say something about the minimal model program for x comma delta. So this is what comes up when you need to study moduli, which we'll talk about on Wednesday. So we'll start Wednesday by kind of how you do this gluing and ungluing, and why it's an issue, and then we'll define the appropriate moduli functor for higher dimensional varieties, and probably end there.